Hello, guys. So how is my exam coming along? Good? Most problems solved already? It's due on the 27th of October. I think that means in 1 week. Right?
Okay.
Now, today we have a huge program and something very interesting to introduce to you. I even yesterday spent a long time modifying some of my lecture notes in hope that you will understand the concept a bit better. But before that, let's quickly talk about independent events. So generally, whenever an event F occurs, yes, it's everything is on the website, you will find it. When an event F occurs, F modifies the likelihood of another event E, correct? So when it actually happens that the probability is not changed, for instance, you see, when I toss one coin, the probability of the second coin coming heads or tails is generally not changed by that information. If I know what happened on the first coin, what happens to the second coin, generally it's not changed. But you cannot assume that, oh, it's very dangerous to assume anything, right? You even have spooky action at a distance, quantum mechanics and all that stuff, and it's probabilistic. So we would say that whenever probability of E given F is probability E, then the events E and F are independent. And another equivalent way of writing it is, observe, guys, if probability of E given F is equal to probability of E, then by definition of conditional probability, this left side is equal to the probability of the intersection divided by the probability F. Yes? And observe what that means. If I just look at this middle equation, at this middle term, and compare it to the right term, I see that probability E and F is the same as the probability of E times the probability of F. That's why intersection, we write it almost as if there is a multiplication sign here. You see, it's very nice to write it this way. First of all, it saves us a lot of effort on symbols. The equation is shorter. It also reminds us why the multiplication rule works in probability. And when you have independent events, it works perfectly. Usually it's a conditional multiplication, right? Usually you can write multiplication, but only if you say something like this. When you say it's probability E times probability F given E. Yes, usually that's how multiplication looks like. But when they are independent, as you can see from those equations, you see this probability is not modified by the introduction of prior event F. But this, by definition, is this middle term. And so rearranging the terms here from here to here, we see that probability EF is probability E times probability F. Agreed? So you understand that this sentence and this sentence are going to be equivalent. You can also see in reverse, because if I divide by probability F, I see that that there was no modification. So what I placed in this red box is equivalent statement to independence, to what we imagine it here. Yes? Of course, we can assume probability of F is not 0. And the reason we assume that is because if probability of F is 0, then such situations are well, you have to be careful when you consider them. In general, when probability is 0, they are not likely to occur. And in general, this statement works for all situations. This works when probability is 0, you know, right? We're just measuring probability. We're not measuring whether something can or cannot happen. We're just measuring the frequency with which it happens. And if the probability of F is 0, then the probability of E given F happens to also be 0. To avoid right, so what we do is we basically now have this observation, guys. If the probability of E is not zero and probability of F is not zero, then we have that probability of E given F. If we know all three statements, the probability of E is not zero and F is not zero, and probability of E given F is probability of E, and then the reverse is also true. Probability of F given E is probability of F. So they are basically, if E is independent of F, then F is independent of E. You see, so nine of them affect the likelihood of the other happening. Does it make sense? So yes, good. So another observation is that, and here is, by the way, that proof first, right? So probability of F given E is the intersection divided by probability of E, but the intersection can be rated as probability E, probability F, and we can cross out probability E and we get probability F. So it's a simple calculation, and we see that this is true. And another observation, if E is independent of F, then E is also independent of F complement. You see, so if F does not affect the likelihood of E, then F complement also does not. Because I mean, it's almost intuitive, because F is a sort of information. Yes, so regarding the exam, naturally, guys, the exam you send to me once you're done on October 27th. Ideally, you do it on the 7th day. Don't try to be too eager. Send the exam on October 27th by midnight, Cinderella time. And you know what it is, right? That's when everything turns to dust. So that's when you send me the exam by email. You know my email, yes? Good. So the other thing is, let's prove this this other observation. So what is probability of E and F complement? That's by definition the probability of E minus probability of E intersect F. You agree? Right? Basically, we know that this is part of E. E can be broken into E and F complement and E and F. So we can then, of course, write it this way. And here I can use the independence of E and F to write them as a product. And here then I can factor probability of E. So you can see that 1 minus probability F is probability of F complement. So again, we observe probability of E and F complement is probability E times probability F complement. Good. Now here is an example. So we have two fair dice, and we toss them, and we have E1 is the event sum is equal to 6, and E2 is the event sum is equal to 7. And F is the event that first die is equal to 4. Good. So we want to know if E1 is independent of F. Well, we can calculate it very simply. Okay, guys. So what's the unaffected probability? What's the general probability of E1? The sum is equal to 6. So how many ways to get 6 from two dice? It's 1 and 5, 2 and 4, and 5 and 1. So you count all the way to 5. So there are 5 outcomes where the sum is equal to 6 over 36 possible outcomes. So this probability is 5 over 6. Yes? And what about probability of E1 given F? If I know that that the first die is 4, then the second die has to be, if the first die is 4, the second die in general can be, if F happened, can be 1, 2, 3, 4, 5. Well, there are 6 possibilities for the second die. Do you agree? So there are 6 possibilities altogether. That's our new sample space, right? That's the new sample space, which is first die is 4 and second die is either 1 or 2 or 3 or 4 or 5 or 6. And only one of the outcomes gives us 6, namely second die must be 2, right? So it's 4, 2. So there is only one outcome in this universe. So it's 1 over 6. And as you can see, those are not equivalent probabilities, yes? So that means that E1 and F are not independent. That's obvious, right? It means if I know that first die is 4, it affects my probability. In fact, it actually makes the probability more likely that the sum is a 6. You agree? Because 5 over 36 is smaller than 6 over 36. So knowing that the first die is a 4 increases somewhat the probability that I got a sum equal to 6. Now, what about E2? E2 is that the sum is equal to 7, right? Would you like to calculate yourself? Before I show you, right? So what I'm asking you guys is to calculate and tell me whether or not the fact that the first die is a 4 affects the probability that the sum is a 7. Good, and I'll be right back. Okay. All right, guys. Not everybody, I see only 4 answers. So let's see the calculation, right? So I think one person said dependent and maybe 1 or 2 said independent. Well, let's look at it. What's the probability of E2? Sum is equal to 7, 1, 6, 2, 4, 5, and onwards, right? So I can go all the way. First, just focus on the sum, on the number on the first die. It goes from 1 to 6. So that tells you that there are 6 possibilities, correct? 6 possibilities, 6 universes. So 6 out of 36 universes give us the probability that sum is 7. Agreed? So 6 over 36 can be simplified to 1 over 6, right? But don't right away simplify. 6 over 36 tells us something, okay? Something important that might prevent confusion later on. What's the probability of E2 given that first die is a 4? Okay, if first die is a 4, we already mentioned, that means that's our new sample space, right? That we know that the first die is a 4, so first is a 4, second is a 1 or a 2, or we have 6 possibilities. So we have only 6 universes now. Do you agree? And naturally, each of them is equally likely. I think we even showed that any restriction of an equally likely sample space to a smaller one results in an equally likely space. And there is only one universe. If the first is a 4, the second has to be a 3. Do you agree? To get the sum equal to 7. So there is only one universe out of the 6 that gives us the summation 7. So the probability is the same, which means they are independent events. Now, why do I say don't right away simplify? Do you observe, guys, that it's not true that the fact that F happens, it's not true that we have no information. We do. Our universes, we used to have 36 possible universes, but now we have only 6 possible universes. So we have a reduction of possible universes by a factor of 6. But we also have the same reduction in the numerator. You see, the information reduces by the same factor the number of possible universes and the number of universes with the desired outcome. Do you see that? So independent is not that you don't get the information. Everything that, as ever mentioned, gives you information about the universe where you reside. But that information might not be affecting probability. That's what we need to know. Yes, so you see the 6 over 36 and 1 over 6. My point is that when an independent event happens, I mean, if F happens and E is independent of F, that does not mean that F does not tell you information about E. You see, everything tells you anything I ever say tells you where you are located. You see, it doesn't matter how irrelevant you think, but every single word uttered of my mouth, everything that you see around yourself in one way or another tells you about the universe where you find yourself in, right? But that information might not help you calculate the probability. It might not change the probability. As in here, this information F reduces the number of potential universes by a factor of 6. Do you agree? But it also reduces the number of universes with the desired outcome by a factor of 3. Good? By a factor of 6, not 3, sorry, right? By a factor of 6. So that means that probability is not affected. Good? And here is a question, guys. So this one is very interesting. Suppose E is independent from N and that E is independent from T. Yes? Is E independent from the intersection of N and T? So you understand? In other words, N does not give any information that affects probability of E, and T does not give any information that affects the probability of T. Is it true or false that E is independent from NT, the intersection? It's maybe an unfair to ask you to do it obviously right now live, but perhaps you can tell me what's your intuition. What do you think? I'll wait 4 minutes, okay? Okay, Gustavo, you're saying that E is independent of N. That's exactly what it means. And also the same calculation would hold for T. But I'm asking, is E independent of N combined with T intersection? Thank you, Chiara. I was hoping you would say something. And good, you see, the brave lead the way. So once somebody is brave enough to be the first, the others follow. Well, guys, let's say, I'm sorry I give you so little time, you understand. I hope it's just not me, the constraints of the class. If I had it my way, it would be 24 hours. So could you please tell me, yes, could you please tell me what is your intuition? I mean, I know Chiara did and Camilzon did. I mean, I'm not sure it's an easy question to answer just right away by calculation, but perhaps tell me what is your intuition. Do you think the answer will be independent, not independent? Okay, Nicholas, thank you. And the others? Sydney, independent. So we are asking, so it means what do you, do I like, I mean, of course, I like not to trick you. I would like you to be trick proof, because I mean, when it matters, I think people are readily tricked, and they don't even see that, right? When it really matters. I do not know if I'm not readily tricked, but at least I'm skeptical, so to speak, right? At least I tell myself I am not convinced, even, you know. Right, so guys, let me now tell you something. Okay, it's very good before going to bed to read fairy tales. Yes, and I always do that. I read Brother Grimm right now, right, because they're very cool. It inspires me. And let me just for a moment show you my true nature for just a moment. Do you see me? Well, you do not see me, but you see my true nature. And here it is in the picture, right? Oh, somebody is studying German. Oh, that's dangerous to tell me. Okay, so let's try to understand how this has to do exactly. Little Red Riding Hood. Yes. Now, what happened in the Little Red Riding Hood? Let's basically see the situation from our perspective. So, Little Red Riding Hood meets several animals on her way to grandma from the forest. And those are 9 animals. 6 of the animals have big eyes, 3 of them have long noses, and 3 of them have sharp teeth. Yes? So having taken a probability class, she can draw the following diagram. Here is the situation. So here, guys, are the people that have big eyes. There are 6 of them. That's E. Yes. And N are the animals with long noses, and T are the animals with big teeth. Now let's look at the situation, guys. What is the probability of E given N? Right? Probability of E given N is what? It is, if N happened, then E contains 2 of the elements. So it's 2 out of, so probability of E given N, it's 2 out of 3. Do you agree? N is the new sample space. We have 2 outcomes that are in E. So it's 2 out of 3. That's the probability of E given N. What's the probability of E in the general sample space? Well, E has 6 elements, and altogether we have 9 elements. So it's 6 over 9. It's again 2 over 3. So you agree that E is independent of N. Yes? And of course, if we look at the T situation, at the animals with the big teeth, right? You see what happens, guys? Having what we just now see is having big eyes is independent of having a long nose, right? It's basically the probability you meet an animal that has big eyes is not affected by the probability you meet one with a big nose. Now, similarly, if you meet an animal with big teeth, the probability that animal has, the probability this animal has big eyes is 2 out of 3 again. So E is independent of T. Do you agree? But E, what is N intersection T? N intersection T is this one point. So the probability of E given N intersect T is 1, guys. So that means that if so you see, you understand what's happening here, guys? Yes, E is independent of N, E is independent of T, but when you take the intersection of all of them together, you get the wolf. Yes. Yes, Nicholas. So no, that is so in some sense, I'm sorry I spoiled your in some sense I prefer to keep you misinformed, right? It's as if you're saying, okay, having big eyes tells you nothing. There is no need to fear more, right? Having big teeth does not tell you to need to fear more. But if you have a big nose and big teeth, then you are going to have the big eyes of the wolf. And in general, how do we define probability to be independent if you have more than two events? They have to have this relationship that probability of any combination of them is just the product, right? So probability E, F, G is the product of them. Probability E and F is the product of them, you see? So that's what independence of all of them means, that any relation you can find will still not cause any probabilistic information about the one event in terms of others. Good? All right, so now it is time to move on to chapter 4. So first, we need to learn an idea that's called random variables, okay? That's the first lecture. So it's not very complicated, and I hope you will all understand what it means. So well, imagine that what we have, guys, is we're going to play Russian roulette. And everybody knows how to play Russian roulette? Yes? So you take a revolver, you place one bullet, you spin the drum, and then you put it to your temple. There is also a very good movie. It's called The Deer Hunter, I think, or Deer Hunter. It's with not Al Pacino. What's the other guy's name? I forget names. Do you know the movie The Deer Hunter? No? Okay. Well, it's with Robert De Niro. Okay. So in a Russian roulette, we have 1, 2, 3, 4, 5, 6, 7. Let's say it's a 7-chambered revolver. In the one of them, there is a bullet. And in the other ones, there is no bullet. And each chamber is equally likely to be the one fired. Do you agree? But for a person playing the Russian roulette, the actual chamber is not very important, right? It's not immediately interesting to you that, well, you fired chamber 2, 3, 4, 5, or any of them, right? What you care about is bullet or no bullet, okay? So a random variable is a sort of guide to translate or morph one sample space into another. What you should imagine is this, right? So we have a sample space S, that's the original sample space, and we have a generated sample space S star, that's the X random variable, just converts S to S star. And you can imagine the actual universes as small stones, and they are, or small pieces of metal, coins or something, that are going to be melted together, and the probabilities, that's their weight, added when that happens. You see, so what happens here? So or you can imagine it as a relabeling, right? So the event 1 is labeled as bullet, and events 2, 3, 4, 5, 6, 7 are labeled as no bullet. You agree? So what's the probability of bullet? It's 1/7. What's the probability of no bullet? 6 out of 7. You agree? Because now all those universes were in some sense merged into the one universe N. Or if you prefer, all those outcomes were labeled as N, right? So this is no longer known as 2, but as N, 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 right? So whenever N happens, maybe it's 2 happened or 3 happened or any of them. So that's why you add the probabilities. But you see, what is the random variable doing? It's nothing extra other than labels. You see, it's just assigning labels to an existing sample space. So you can either think of it as a separate sample space, or you can just think of it as the original sample space with different labels. There is nothing random about a random variable. Do you agree? Because we are not asking what's the likelihood that something happened. We're just assigning different labels to the universes. We're just renaming things. Is that clear? So how do you calculate the probabilities of this random variable? Is you just you want to know, for instance, what's the probability that of P of X? What's the probability, let's say, that an event Y happens, right? So an event Y might be this. This is the event Y, right? What you do is you see all the universes that contributed to this one outcome, and you add up their probabilities, right? So for instance, in this example, what's the probability that B happens? Well, you see what could have led to B. That's only one universe could have led to B, and that probability is 1/7. But if N happens, what is the probability? How can it happen? It's this or that or that or that or that. So you add the probabilities. Is that clear? So you just take, this is what I write here. Probability of Y is the inverse image under X, and take the probability of that. The inverse image is a set. So you understand what that means, guys? I hope you know this notation. That just means trace back. So look at this thing and trace all the fibers back to where they came from, and then you recognize the actual universes that could have happened, and then you have the actual probabilities next to them, and you add them up. And that's what I'm saying here, okay? So here is an example. 3 balls randomly selected without replacement from urn containing 20 balls numbered 1 through 20. If we bet that at least one of them chosen balls has a number as large or larger than 17, what's the probability that we win the bet? Okay, so we can describe the largest ball as 3, 4, 20, right, all the way to 20. We just decide to name this, right? And we can now describe those events instead of, so there are 2 useful things about random variables. Instead of writing sets, it can be very tedious to write sets. You can now write a sort of like an equation. So we are interested in probability X being bigger than 17 because X is assigned to be the biggest ball selected, right? So what do we have here? We have a sample space here. A sample space consists of 20 choose 3 universes. Do you agree? 20 choose 3 universes. Each universe tells you the denominations of the balls that were picked. Do you agree? And what does X do to each of those? It picks up the biggest one that you have there. You agree? So then we want probability that X is bigger than 17. Well, that's the probability that X is 17 plus X is 18 plus X is 19 plus X is 20. You agree? Now, what's the probability X is 17? That means the largest is 17. Well, it's then I can choose 2 balls from any number smaller than 17. So 16 choose 2 divided by 20 choose 3 is the probability here. Yes. Now this probability is 17 choose 2 divided by 20 choose 3, and so on. Do you agree? And I then add them up and I get this number. Everyone understands? Right, guys, it's an important point. Please write Y or N just to be sure that I don't move too fast and I know that you're following me. Why choose 2? Okay, very simply, because 17 is the largest. It's already there. Guys, it's a Kafka protocol, you see? So 16 over 2 divided by 20 over 3. It's already, the question is already one that we solved many times. It's Kafka protocol. Yes, so denominator tells us all the possible universes. There are 20 choose 3 universes, right? Every time we play this game, and probability X is equal to 17 means I have 17 and I have every other one is smaller, right? So I already have 17. So in my Kafka protocol, when I list which numbers I have, 17 is filled in and I have room for additional 2. And those 2 must come from the first 16 balls. Agreed? So this is just me, you know, you do Kafka protocol and you do Kafka protocol in your mind sometimes, right? But you have to be careful. All right, so here is another example, guys. I don't see 19 answers, right? So come on, right? You're not that lazy, right? Y or N? Good. So yes, random variable, just a fancy name, but what it means, relabel sample space, right? Or if you prefer to think of it, melt universes together into sample spaces stars. So it's a new sample space generator. I tend to think of it in both ways, either melting or just the same original thing, but with different labels. That's all it's doing, right? just the labeling, giving universes different names, and sometimes the same name to several universes. Good. So here, x equal to 17, it's a name of several universes, right? X is 17. Those are actually 16 choose 2 universes that carry that name, right? 16 choose 2 universes, that's 16 times 15 divided by 2, carry the name 17 by this new relabeling. You understand? Because in those universes, they have the property that the biggest denomination is 17. Yes? So a fair die, new example, fair die is tossed until it comes up 6. Let x denote the number of required tosses. You understand? So we are going to throw the die until we are successful and we get the number 6, I think, yes? And then we see how many tosses. Well, we could have gotten 6 on the first toss, you agree? And the probability of that is 1/6, right? Or we could have gotten it in 2 tosses. That means first toss is a failure, second toss is a success. There are 5/6 ways to fail and 1/6 ways to succeed. So here I can multiply it. I'm using the product, right? I mean, the second throw of the die is not influenced by the previous one. Do you agree? So I can imagine, for instance, that what is x2? X2 means failure first, not failure second. Yes, not failure means we don't pick up a 6, and failure not means we do pick up a 6, right? And the probability of that is the probability of F1 times the probability of F2 complement given F1. And F2 complement, right? They are independent events. You can clearly see that, right? The probability is not affected there because the outcome on the first die is not influencing the probability. So that's probability F1 times probability F2 complement, right? And probability of first die coming up 6, sorry, not coming up 6 is 5 out of 6, yes? And that's why I multiply. So we have, in general, probability that the first success is on the nth throw, means I have n-1 failures, and they're the same. So it's multiplying 5/6 to the n-1 power. You can also do it as a full sample space. You can imagine that, right? And multiplying it by 1/6. And so the probability that finitely many throws are necessary is the probability that x is a natural number. And when and it's either 1 or 2 or 3 or 4 onwards, so it's the summation of this infinite series. And this infinite series, as you remember, you know how to sum geometric series fast. Do you agree? I taught you how to do that, I think, in lecture notes. So you should know how to sum series fast, and this equals to 1. Yes, this series is equal to 1, which means that the probability that we will need infinitely many throws is 0. Yes. Does it mean that infinity cannot happen? It's exceedingly rare to happen, right? For sure, right? So you will never see, in this case, you will never see infinity happen. Okay, so now we can talk about discrete random variables. So the word discrete, if you studied analysis, means that the elements are not uncountable. So they're countable, to be precise, right? Countable means you can put them. They're either finite or you can pair them injectively with the natural numbers 1, 2, 3, 4, 5, 6, 7, right? And onwards so the integers. So that means they can be placed in a queue line. So first in line, second in line, third in line, all the outcomes that x can take. And for those, we can then, of course, describe the probability mass function. The probability mass function is just, it's assigning a probability to each of the x1, x2, and onwards, right? So there are only countably many that can have a non-zero probability. Every other x has a 0 probability. And those are assigned some value. Okay. And of course, the summation must be equal to 1. The summation of all the values xn must equal to 1 for a very simple reason, guys. So you see what a random variable does. It's just a different label. We're still in the same sample space, you might think. And so those probabilities, you see, however you label them, must add up to 1. So all the new labels, one of them will occur. So with probability 1, one of the labels is actually the outcome when you run the experiment. So when a fair coin is tossed 2 times, x is the number of heads obtained. I mean, I should have not drawn a histogram. It's actually better to draw maybe a thin line, because it's either 0 or 1 or 2, right? I mean, so it's nicer to just draw a stick, I think. But okay, so the probability of 0 happening, it's probability of tails, right? I mean, x represents the number of heads. So if x can equal to either 0 or to 1 or to 2. Probability x is equal to 0, it's the same as the probability tail. So tail, the actual universe is tail, it's labeled as 0. Probability tail heads and heads tails are each labeled as 1, and the probability head is labeled as 2. So you see, again, we have the same universes. We have 4 of them, but we just have named them differently. So this is labeled as 0. This one is labeled as 1, and this one is also labeled as 1, and this one is labeled as 2. So probability of 0 is 1/4. Probability of 2 is 1/2, because there are 2 of them, 2/4, and probability of 2 of x being equal to 2 is 1/4. Agreed? Simple example. And here is another example. Let's see if you can help me with it. So imagine that x takes the integers 0, 1, 2, 3, and onwards, and the probability with which it takes those integers are c, some number c, times lambda to the n over n factorial, right? And can you figure out what's the probability that x is equal to 0? So you see, basically the number is the power here, right? N is 0, 1, 2, 3. So what is x? What is the probability of 0? And then what's the probability that x is bigger than 2? What is C, Nicholas? You are correct, but we need C. Well, of course it's a constant, but what constant is it, right? All right. Very simply, guys, you have to remember that the probabilities have to add up to 1. Do you agree? So, I mean, you can describe C in terms of lambda. So what's the summation of this thing? When I add all of them, that it equals to 1. What's that summation, guys? Well, let's look at it. 1 is equal to, I can factor the C, and this summation here is just e to the lambda, yes? So 1 is equal to c to the lambda, so c is equal to e to the minus lambda. So probability of x being equal to 0 is e to the minus lambda, lambda to the 0 over 0 factorial, and that becomes just e to the minus lambda. Lambda is the number. We are going to describe those things later on. This is something very important called Poisson distribution. We will talk about it at length. pretty interesting distribution. Okay, it involves E all the time. And then we can calculate probability that X is bigger than 2. And easiest way to do that, we can of course sum up 3, 4, 5, but that's an infinite series, so we can go the other way around. It's 1 minus the probability 2 or less, and that's 1 minus probability 0, probability 1, and probability 2, which is what you see over here, right? I just plug in lambda 0 over 0 factorial, lambda to the 1 over 1 factorial, lambda to the 2 over 2 factorial, and that's my C. E to the minus lambda is the C that I calculated. Good. And then I have to talk a little bit about the cumulative distribution. It's a very interesting topic once it comes to continuous random variables, but I don't understand what's the importance of it in other contexts. So if it's a continuous random variable, which we'll talk about later, I can tell right away what's the use of it. But here, for the love of me, for the love of God, I don't know. So probability, basically we sometimes want to know what's the probability that X is less than or equal to A, right? In other words, that the probability of something less than the number A. I mean, maybe if you are a very good student, you want to know if you're in the 99th percentile, right? So that relates to this distribution. For it, that means that that 99% of everyone scored lower than you have, right? And so that's this type of function. It basically given the value A, it evaluates the probability that X is smaller than A. But when you have an outcome, it will be not as big as A. Okay. So in the discrete case, what do? You add up all the probabilities for which the outcome is xn, and xn is smaller than A. Yes. So for instance, suppose that X has the probability mass function, where probability of 1 is 1/4, probability of 2 is 1/2, probability of 3 is 1/8, and onwards, right? So then you can see how the function works, right? This cumulative distribution is going to just ask, okay, what's going to happen if A is smaller than 1? You see, 1 is the smallest number that actually has some probability. So if A is any number smaller than 1, the probability of that is 0, right? So it's 0 probable that anything will come out that's smaller than 1. Now, what's the probability that if A is bigger than or equal to 1 but smaller than 2? Right, so that means suddenly once I skip over 1, that is 1/4. You agree? Until I gather 2, until A is bigger than 2, I can only pick up 1. Basically, I sweep to the left. Right, I sweep to the left. So I give A and I sweep to the left, and I find all outcomes that have non-zero probability, and I add those probabilities. That's what this is telling me. So this is 1/4. Now, if I include or am bigger than 2, then 1/4 and plus 1/2, because then I pick 1 and I pick 2 and I pick their probabilities, so they add up. And if A is between 3 and 4, I also pick up the 3. And if A is bigger than or equal to 4, I pick everything. All right, and that will be 1. This number has to be 1. So the cumulative distribution eventually, either it's growing forever towards 1, or eventually it reaches 1 and then it's flat. Here are the steps. You see here, if A is any number below 1, I don't pick any outcome that has non-zero probability. Once I skip 1, I pick the 1/4. And notice that I don't pick anything. That's why the line stays flat. I don't increase in probability. But once I reach 2, look at it, at 2 there is a junction. If I'm slightly below 2, I only still pick the outcome 1 and its probability. But as soon as I jump to the right of 2, just move slightly to the right of 2, I pick both outcome 1 and outcome 2. So I pick the combined probabilities, right? And that adds up, and the probability 1/4 plus the extra probability from 2 add up to produce this probability. And notice by the time I reach 4, I become 1, and it will forever be flat. So it's a step function. Okay. Oh, and now we come to the problem of expected value. And because of that, for you to understand the situation a little better, I wrote separate notes because it will come in handy, I hope. So those are the notes. So let's try to motivate this new concept where you use the random variable so frequently. So suppose that you have this addiction to play certain Wheel of Fortune games, and you come to this carnival and you see the following game. The game has this wheel with 5 slices, equal slices. And if slice 1 comes out, you are paid $20. If 2 or 4 come out, you are paid $50. 3 or 5, you are paid $100. In other words, if the outcome is any 3 or 5, you get $100. Now, the price of the game is $65. Yes? What will happen if you decide to play this game and make a habit of playing that game? That's what we want to understand, okay? Now, let's look at that very carefully, okay? So first of all, we have a random variable. The random variable is labeling the outcome. So what outcomes can I have? I have outcome 1, 2, 3, 4, or 5. That's my S, right? S is the universe. The universe is black or orange or green or whatnot, right? And X of S is how much money I win minus 65, because I mean, I don't care that I just won $20 if I lost 65. Do you agree? So you care about net gain. Net gain is win minus 65. Agreed? So we can imagine playing this game for several rounds and see what outcome we get. So here is, for instance, that game. We have 5, let's spin it now. 5 outcomes. Exciting, huh? What are you gonna get? And you get 4. Yes, you got 4. So what does 4 correspond to? 4 corresponds to winning, what is it, $50, right? So you won $50, congratulations. So you give me 65. I'll give you 50. Good. So let's say the gambler plays this game, and he decides to play the game on 2 weekends, on 2 weekend days. So this is Saturday, this is Sunday, right? And the gambler decides to play the game for how do you call it, 20 rounds, right? 20 times. Okay, so here's what happened after 20 rounds. I actually, spun the wheel and recorded the outcomes. Okay, so I colored them, and you can see here are the pays, right? Here are the money that you won. Minus means that the net is lost, and 35 is when you get 100 and onwards. So on Saturday, altogether, you lost $50. The next day, he comes again, and this time he was lucky. He won 130. Right? So next day, this is the game, and the price was 130. Okay, is it worth playing the game or not? Still not clear, right? One day you lost, and then the next day you gained. Altogether, you gain money. Do you agree? I mean, 130 minus 50 is still positive. So the gambler actually had a good weekend, earned some money. Yeah. Let's see what happens when the gambler plays 100 games, right? So, and we simulate doing it habitually. So let's say this is 1 run, 2nd run, 3rd run. You understand what it means? Yes, it means that we go for the entire day. He plays 100 games. So he played 5 days, and each day he played 100 games. So look what happened here with 100 games. You have first day he lost $260, second day he lost $480, third day $50, fourth day $470, but on the 5th day he won 40. Sometimes you still win. And this in red is the average per game. You understand? So if you just if you get minus $260 on average per each of the 100 games, you spend $2.6, right? So the outcome would have been the same as if each game he just enjoys watching. He's autistic, he enjoys watching the wheel spin, and so he likes to pay money for it, right? Some people go to strip bars, but he goes to watch the wheel spin, and then he pays $2.6 for it. Good. And then on the next day, he had to pay for game $4.8. But in this in round 4, he actually got 40 cents per game. That's 100 games. You see, guys, what I do for you? I sat yesterday and I spun the wheel 500 times. Yeah, just sat there and clicked all day long. And then, of course, what is the calculation? You understand how I carry this calculation, right? So here, because it's 100, I, of course, did not want to produce 100 columns. What did I do? I just grouped based on the number of occurrences of each outcome. So outcome 1, in this case, occurred 17 times, outcome 2, 26, and so on, right? You see how often each outcome was happening here. So I basically collapsed the table, gathered all outcomes together so that the table is visible. But if I wrote it this way, it would be 100 rows long. Yes. And then how do you calculate this number to minus 260? Well, you take the number of occurrences on the number of outcomes of type 1 times the payout. X1 is how much you get paid for one, right? And for that you get minus 45, sorry, right? And then plus number of times 2 happens times the cost of each of them. And you understand this formula. Great, guys, you understand this formula. I don't need to overly explain it, correct? You see, this is just the number of times S happened, and this is the payout or payoff. And then the average, what you do is you just take that number and divide by number of games, and then you get how much you get per games, right? So then, guys, of course, I was not lazy, and after doing it 500 times, I did it 50,000 times, right? I don't have anything better to do, you know. So I actually, well, so you see what happened, right? So I spun the wheel 10,000 times for each round, and now look what happens. This time, those are the outcomes, and look at it. The loss for paying 10,000 games. In this case, he lost $4,340. In this case, 10,000 something dollars and onwards. You can see quite lots of losses. And on average, you can see those numbers here. Still, it's not so terribly clear what is happening. Maybe not absolutely clear, correct? I mean, you have certain numbers, they are negative, but what's happening when you play those games, when you make a habit, right? So this is a habit, but maybe not addictive enough. Okay, let's see what happens if we play 1 million games each. You see, guys, what do? I didn't sleep in at all, right? I played afterwards at night, 5 times a million games. 5 million games. So what you have is this time, look at the losses, right? They are all essentially close to $1 million, essentially almost $1 million. And this is how much is lost per game, you see? And you might suspect that the average payoff approaches what number? What do you think? What do you think happens as I play more and more games? Well, I mean, as I play more and more, look at it, right? I already played 1 million. Now, what happens if I play 10 million, 20, 100 million, and so on? And what happens if the number of games goes to infinity? What do you think is happening? Yes, you can see -1. It appears to be -1. Let's verify why it's not a bad supposition that the limit will be -1. Yes, the limit will be -1. Well, look at it. In general, imagine I play n games and I push limit to infinity to indicate that the number of games grows. You agree? So it's going to be n1 times x1 plus n2 times x2 and onwards, right? You see this formula, and I don't need to over-explain. You agree? You understand what it means. All it is just the number of outcomes of each type times the payoff you get for the type. So in other words, I collapsed this table. I could have had 1 million rows, but instead I just grouped how many times did I get, look at it, how many times in round 1 did I get outcome 1? It's very close to 200 times. Each of them is very close to 200 times, 200,000 times to be precise, right? In each case, each is very close to 200,000 times. Yes. Now, if I look at this limit, guys, I can write the limit as n1 over n times x1. That's just the payoff; it doesn't change. X1 is not changing, right? And 2 over n times x2 and onwards. Now, each of those, you recognize this is a limit, right? What is that? This is the probability limit. You agree? Now, what's the probability limit of a wheel if the wheel is fair that has 5 sides? That the limit has to be 1/5. You agree? We expect this limit to be 1/5, and that's why we see the number here. If you divide it by 1,000,000, it would look like 0.2, which is 1/5. So that's what I wrote over here. That's because the limit for nk over n is 1/5. You can actually simulate. You can simulate the situation that you can see how fast the convergence is happening. It's not so terribly fast. You agree? So you can see the convergence on the spinning wheel, on the wheel of fortune, is very noticeable once you have million rounds. But if you play one game, it's not so noticeable. 2 games, not so noticeable. Even 10,000 games, I mean, begins to be noticeable, but not so terribly noticeable. You have to play many games. You really have to make a big habit out of it. And those numbers they're going to be what? They're going to be 0.2 times minus 45 plus 0.2 times minus 15 and onwards. And you get the number -1. Okay. And what does the number -1 imply? Well, it tells us that Fortuna is going to abandon you if you develop a habit. If you play, and that's a good advice. You read Dostoevsky, you read The Gambler, you play, you're a novice, you play once, you take your money and you leave, because Fortuna is not going to be kind to you if you make a habit, right? It's going to be absolutely deterministic. And why is it going to be deterministic? Well, if you believe in the running frequency interpretation, when you play many games, nk over n is going to approach 0.2. So that means if n is very large, here is the theoretical estimate, right? I took it from column 3. I took it from this run. You can see that that this is the theoretical estimates, and you can see that n1 over n, when n is 1,000,000, when it's a big number, it's very similar to the limit. It's very similar to 0.2. All of them are very similar to 0.2. Do you agree? Very similar to 0.2. So that means that when they are very similar to 0.2, the average per game is going to be very similar to -1. Right? So that means if you play 1,000,000 games, you expect to lose $1 million. That's what the average is telling you. Good. Now we need to discuss the definition of expected value. We'll do it in several ways, and I hope the columns are helping you. It's interesting, right, guys? Right. So you see, it's very good to simulate those things to have a sense of how quickly is the convergence is happening, and what is a habit, what is the habit doing. But so far you understand the idea, correct? Right. So expected value is calculating the average payoff. That's what I try to say here. So I said something rather fancy, but hopefully you understand it. The intuition is very simple. Expected value is a metric that measures the average consequence of a random action when this action is performed repeatedly. So specifically, when we are given a sample space S and a random variable that carries S to S star, in general, the random variable will be the number that usually it's useful to label it with either numbers or vectors. So it could be Rn, it could be R2, R3, R4. You know, it's useful to label the elements in the sample space with some sort of number. You know, for most cases, it's just R. Well, until now, for us, most cases are going to be R, but you have vectors. Sometimes it's important as well. And the expected value is, we can define it as the weighted average. You see what it is? It's just the label of X multiplied by the probability of S happening, right? So for each outcome in the sample space, I add up the product of the value of S times the probability of S. And the reason I do that is, as you can see it in this formula, right? You can see it in this formula. If you just take the average of scores when you're playing a game, you just see how many times the outcome came around, and then this is the label. That's the price that's the payoff you get, and you can see what you get. You get the probability multiplied by the label. Probability of the of a particular, this is the probability of 1 multiplied by its label. Probability of 2 multiplied by its label. So that's what this formula is telling us. Good. It's going to be very important. So I mean, I want it to be tremendously intuitive for you guys. So far, good, yes? And then we're going to go back and do the calculation yet again, guys, because I want you to see something rather incredible, okay? So, and also, once you think about it, it's very easy. When you do expected value, I want you to imagine a giant table or a table that's compressed like this, right? So it's either a table that I had initially with the trials, but the trials are not so important. You can imagine collapsing each time the same outcome comes around, you collapse the situation. You collapse this number together, right? So for instance, this is the experimental. So I can take the table, and of course, you know that I can sort the table based on each column, right? I decide first here to sort the column based on outcome. I'm going to use the first column to sort. Yes. What's going to happen if I sort it by the first column? Well, this is the experimental value. I took it from column 3 with 1,000,000 outcomes. So imagine I simulate 1,000,000 outcomes. So 1 happened this many times, 2 happened this many times. Altogether, we had a million games, right? So this about 200,000 games yielded to about 100,099, right? About 199,000 yielded the outcome 1, and so on. You understand, right? Altogether, total games is 1,000,000. This is the estimation of the probability, right? How do I estimate probability? I take the number of times something happens, divide by total trials. So that's my probabilities. They're all close to 0.2. Probabilities must add up to 1. Naturally, they do. Because again, this number over 1,000,000 plus this number over 1,000,000, right? If everything is done correctly, it always 1,000,000. The summation is 1,000,000. Yes? So the probabilities therefore add up to 1. This is not important what this is adding up to. I just wrote it for the third point, but those are the scores. 1 corresponds to 1. Was relabeled as -45. 2 was relabeled as -15. 3 as 35. 4 as -15. So this is just a relabeling function, yes? And then here you have the product of the score times this probability, yes? It's basically of this column times this column. You agree? That number, what does it represent? It represents the average that you got XS, right? It's the average there. You understand why we need this quantity, correct? And when I add it all up, I get roughly -1. And here is the ideal situation, right? If the table was tremendously long, in fact, infinitely long, you understand? Imagine this table is not 1,000,000 rows long, but infinitely long, and then I collapse it. And when I collapse it, I will see that each of those outcomes is collapsed to 0.2. The outcomes here, this goes to infinity, so it doesn't matter. I just take always the ratio of each to the total. And so I just delete it, and I see that those numbers approach 0.2 each, and they add up to 1. The labels are still the same, and the product is now those numbers. That's what they converge to. And then when I add them up, I get 1. I get -1. That's the ideal situation, correct? Before you go, guys, let's try to finish this quickly. There is a very important rearrangement, which I try to draw to you, and we're going to use it. If you don't get it, guys, you're going to have a lot of problems with what comes. I can also describe the same average by rearranging it in terms of the payoffs. Okay, so I begin again with the same table that I had experimentally. Here it is. And then look at what I'm going to do. I'm going to sort it based on the scores in XS, you see? So I'm going to sort those numbers. You see, you can see repetitions, -15 and -15, 35 and 35. And I want to sort them so they're in order. Do you agree? So what did I do? You can see now S is in different order. I resorted it. 1, 2, 4, 3, 5. Yes? I resorted it, and then I can further, if I want, I can collapse. I don't really want 2 and 4 are separate because they are labeled the same. So if I collapse, what happens? I just have here x. This is not collapsed. There's only one thing labeled as minus 45, but 2 and 4 are labeled as minus 45. So I add up the outcomes, right? Of outcome 2 and outcome 4, I add them up, and here is that number. And outcome 3 and outcome 5 are collapsed to 35. I add them up. You see? And I do the corresponding additions here. You see? And what do I get? I get still the same exact average. If I add those numbers, I still get the same thing. But this is telling me to add based on the score. The score of x times the probability that score happens, plus the score of another x times the probability it happens. It does the addition in a different way. That if you didn't see me doing that, you might be surprised. You might have, and I know you would have, calculated something in a tremendously tedious and difficult way. Maybe you still will. And I can do the ideal table, and I can do the same sorting again. Yes. And this is the table I get. Right? I get probability 0.2, 0.4, 0.4, and I get this number times 0.2 plus this number times 0.4 plus this number times 0.4. Okay, I do the same exact addition, but I do that through a different sorting of table. That's the important part to get. Do you want to listen to the last part 7, or you are too tired? 2 minutes beyond my lecture time, and do you want to go home, or do you want to finish it off? Please vote quickly. You can say yes to listen and to go home. All right. Okay. Then if it's a recorded, I guess, guys. So some people say yes. I suppose we do this. Those that want to listen, you stay, and those that don't, goodbye. It's recorded. I'll post it online, and we'll talk about it more. So here is what I can say, guys. So in general, let's now do the same calculation in general. This is what I just said. In general, suppose that we have scores or payoffs x1, x2, all the way to xm. Those are the payoffs, and x is just relabeling each outcome in S in terms of those payoffs. So the expected value can be calculated as the limit of the sum of the payoff for S times the number of times it occurs divided by n, and I take the limit. Right. The reason I take the limit is that with the limit it becomes deterministic. Yes, and of course, what can I do here? I can push in the limit, and it's xs times this limit, and that becomes summation of xs times ps. In other words, the payoff for getting s times the probability of getting s. So this formula is, I hope, is very natural to you, right? Right. So that formula, what it means is, in our example, it's this. This and formula is this thing. You understood how we got it, yes? Now we can rearrange this. This rearrangement table corresponds to this rearrangement of the formulas. You see the same summation here can be written as, I can regroup it. I can say, okay, let's regroup it by all the x that produce x, all the s that produce x1, all the s that produce x2, and onwards. And that's how the regrouping can be written in formulas. So it's summation from 1 to m, because we have only those outcomes, of xk times all the probabilities. Yes, and that gives me this formula, which looks very differently. And in fact, many of you would use this formula. That's the definition. But when you use this formula and don't realize it's equal to this one, you will make a lot of very complicated, tedious calculations, many of which you will never be successful. It's very important. This small thing, by how you sort, affects tremendously your ability to calculate expected value. Yes? So this formula is the same as that formula. To explain again, how does it work in our situation, guys? This is the way it works in our situation. So the first formula tells us just sort by the outcomes in S. So this is outcome 1, outcome 2, outcome 3, 4, 5. Yes? That's this formula here. Now look at the summation, guys, and you agree that I can group things together. I can keep minus 45 times 0.2, but 15, minus 15 is, there are two of them. So I can group this with that, and I can write this minus 15 times 0.2 plus 0.2. Yes, that's what I'm saying here. You see that's the summation here. All the s such that xs is equal to xk. It's just rearranging the sum and making it look like that. You see? This is the score. This is x2 in this case, multiplied by the sum of probabilities that lead to x2. Right? And similarly for 35, you see, I take 35 and I regroup it. And in this form, it looks like this. It looks like a score multiplied by the probability that you get that score. Do you see? Look at this line and look at that line. When it's finite, it's easier to see that you can rearrange, of course, but when it's infinite, it's a bit less easy to see that you can rearrange. Tremendously clear, yes, because guys, you will see on the exam, and you will see how effective is this observation. You might think, big deal, you're just doing the same addition in 2 ways, but if you're realizing it, first time I realized that was first time I realized I was so surprised, because you have tremendously difficult calculation. The way this is the definition. This is the definition in your book. That's how expected value is defined. So you use this definition, and you get sometimes tremendously complicated calculations. And you switch to a different summation, to a different form of it, and the calculation becomes very easy, because it will have very important consequences later on. We're going to mention them. Good. Thank you for staying. Thank you for listening. Auf Wiedersehen. Take care.